I'm really pleased to be here. Before I begin, I wanted to congratulate you as well as thank the organizers of this meeting. The one that I know best who's been at all these sorts of meetings in the U.S. is Lissa. Kevin and Lisa and Mark here are obviously recapitulating this really wonderful thing, which is getting organized. But of course, I want to tell you the incredible resource that you have is Dr. Rustam Karanja. Rustam and I have been together for, I guess, about 5 or 6 years, working shoulder to shoulder on the issue of Leber's. And when I say Leber's, I mean Leber's hereditary optic neuropathy, a distinction because there are other Leber's out there, and once in a while you'll be misled when you read a newspaper article that's going to say Leber's something else, so be careful. But what should be said, first of all, is that getting together as an organization, as a community, is unbelievably important. Of course, you're going to be supporting each other. It may not be so obvious that this is a tremendous resource to support research. You're going to be providing logistics that will help politically, convincing various organizations to be more receptive to you and to the researchers in the field. You're going to be providing resources to each other and resources to the scientists that will make a huge difference. And Lissa certainly has, taught me a lot of things about perspectives that I hadn't considered, but also have been an incredible assistance in my own work and research. The registry idea is a great idea at so many different levels. And most of all, of course, you're all inspirations, and getting together, it's all the more amazing as an inspiration. So I know this is your first meeting, but I hope to see and hear from you for many, many years to come. Maybe a few more trips to Canada in my future. I'd like that. I'm in Canada now in part because Rustam has organized another meeting. Every 12 years, the Canadians organize themselves for this huge meeting in neuro-ophthalmology called Sally Letson. So in the last few days, I've been doing that. So I'm sort of trying to shift gears this morning to accommodate you. If I'd given my own introduction, I would have made it a little simpler. I would have said, I found out about Leber's hereditary optic neuropathy about 40 years ago. And since that time, I've just been absolutely transfixed by this disease, amazed by the science, amazed by the medicine, and amazed by the patients and their will. So for all these things, it's inspired me, and my research has pretty much been about that. Now, as I say, it's a great pleasure for me to give this little talk. We'll call it Leber's Hereditary Optic Neuropathy 101. And in order to give it, I put together a few slides, which I guess will be coming up in about now. But these slides were prepared initially and taken from various talks for scientific audiences. So maybe even before I begin that, I'd like to make this as relevant as possible to you. Some of you in this audience have been to my office, and so you know how I do it. I sit down and I try to cover 3 topics. And I thought, why not just cover them right off the bat so we make sure that we cover what I think are most important 3 topics. Then we'll go down the slides, and if the slide is a little bit too detailed, okay, we'll just slip by it quickly. But the 3 things that are most important for patients who have this disease to understand is the genetics of the disease, the risk factors for going blind, and what sort of immediate things you can do in terms of treatment. We'll go into long-term clinical trials in the talk, but what is relevant to you here and now today? In regard to the genetics, most of you in high school biology remember that we have about 25,000 or so genes, and actually twice as many because there's 2 copies of each one, and 23 chromosomes, half from the father, half from the mother. Forget it. All that's irrelevant. What matters is a little speck of extra genes that are not in the nucleus, not part of the chromosome system. And those genes live in the mitochondria, these tiny little workhorses that produce the power, the energy for the cell. Now, the mitochondria have a few more genes, but all that really matter are 13 of them, and these 13 genes power their own system. They have to be made internally because the protein products that the genes make cannot cross membranes, and all the good stuff in a mitochondria occurs inside this membrane. The other thing to keep in mind, weird as it is but scientifically fascinating, is that mitochondria were once external. They once were bacteria. 2 billion years ago, they were bacteria that were living in parallel with our ancestors, which were also just one-cell organisms. And the 2 were at war with each other. And they would use chemical means of killing each other and devouring each other. Our ancestors were called eukaryocytes, and the old bacteria were called prokaryocytes. Never mind that, except that one day, instead of being at war with each other, they got married. And one of those little bacteria entered into one of our ancestors, and they discovered that collaboration was the answer. They got along so well that they could prosper better than anyone else, and that became the dominant life form. At the time, the bacteria had 1,500 genes, but all the genes but 13 could go back and forth, and therefore our answer, eukaryote, was better at doing these things, so they all moved into the nucleus, but left behind these 13. Now, fast forward 2 billion years. One of those 13 gets mutated, and that's your disease. That's Leber's hereditary optic neuropathy. And actually, the mutation can be at different places on the gene, so that's why you get these numbers. So you can have the most common form, 11778. You can have the perhaps brutal form, which is just more serious, 3460. Or if you're really, really lucky, you can have the light form, 14484. So there's a little difference between them all, but not in terms of the genetics. The genetics are, because they come from the mitochondria, they come only with the mitochondria. And that means 100% with the egg. That means 100% with the mother. And jokingly, I say if a mother who is a carrier, and that's what a carrier means, you just got the gene and nothing more, has 1,000 children, 1,000 will be carriers as well. It also means that if you're a man, blind or not makes no difference, you do not contribute mitochondria with the sperm, so there will be no passing of the disease. And that may be obvious to you, but it's worth emphasizing because I have run into patients occasionally where the man is thinking about not getting married, not having kids, and saying, well, this has zero effect on the likelihood of your children having this disease. So that's the fundamental genetics, and that makes you a carrier. One of the great oddities of this disease is that most carriers have no vision problems. Just having this genetic mistake is not enough to cause blindness. The phrase that I coined maybe about 40 years ago, but I think is fundamental to understanding this disease, is the mutation is necessary but not sufficient to cause blindness. So what is sufficient? And it's probably one of 3 different things. Either that you have in this background of DNA, the regular stuff that makes you have blonde or brown hair, all these other things, other little factors that nudge in one direction or in another. So it's sort of predestined, but it will influence whether you have a breakdown in things or not later on. The second thing is the background DNA in the mitochondria. There's more DNA than the one that's mutated, and some of it can be supportive and some of it can aggravate the condition. And we call that the polymorphisms or the haplogroups that exist in the mitochondria. And the third, this one is under your control, and that's the environment. So in the conversation I have with all my patients, we emphasize tremendously what are the risk factors in your environment. And right here, I do want to emphasize the big 3. First and foremost, smoke. Smoking, of course, cigarette, pipe, doesn't matter what, but smoke in all forms. Some of you will remember I almost always say the same thing. You can go ahead and eat barbecue, you just can't be the barbecuer. You got to get away from that grill. I even teach the kids the technique of licking your finger and holding up to see which way the wind blows, and you walk upwind of the barbecue. It's not eating the stuff that matters, it's breathing in. And so you want to stay away from smoke, even to the extent that if there's a big fire nearby, you should not be the one to go watch it. You should go the other way. And if you want to keep warm, and on a winter's night, it'd be nice if you didn't do it with the fireplace, because any form of smoke can be the trigger. And by the way, the trigger doesn't usually cause blindness right away. There's usually a lag period of a couple months or so. And so we have had a number of cases where people were involved in a faulty stove or a tire fire or other exposures to flames, and it was a few months later that members of the family would all lose vision as a consequence. Now, one of the peculiarities of this disease is that it affects the genders differently in 2 ways. We mentioned one already, which is that you can only pass it if you're the mother, not the father. But the other one is that estrogen is a friend. It pushes the genes in a good direction, and men don't have much of that. And so men are more likely to become affected. Affected is the conversion from carrier to blindness. And so we mentioned that there's several things that can flip you in that conversion, these risk factors, but there's several things that can prevent that conversion, and one of them being estrogen. So I mentioned that for 2 reasons. One is you've heard that it's more likely that young men are blinded than young women. But by the way, only 3 or 4 times more likely. It's not an overwhelming factor. So women should be really careful too. These risk factors have to be avoided by women because not only you're not immune from the disease, it happens regularly. But in addition to that, I would strongly urge all of you who are approaching the age of 50 to have conversations with the OBGYN. He doesn't know better, but you want him to understand that you should not go through menopause. I think menopause is dangerous because it takes a woman's odds and makes it the same as a man's. And so invariably, no, that's not quite true. Quite often, when I give this message, I get a call or a letter or a message from the OBGYN saying, you must be living in the 1970s. We don't give estrogen to prevent menopause anymore. And I say something along the lines, more politely than I'm telling you now, that back then, everybody was given medications to avoid menopause, and the argument was that it helped you with the osteoporosis. True. Then it was discovered that it also was a bad thing because it could either aggravate breast cancer or increase the risk of heart attack and strokes, and everybody stopped. And both of these have truths, but the biggest truth of all is it depends. Each individual needs to be assessed. If there's a lot of breast cancer in your family, you probably don't want to go on estrogen. I get that. If there's tremendous issues of osteoporosis, maybe you do. But one of the biggest issues that possibly could be to help decide one way or the other on this one is whether you're carrying the LHON gene. My goodness, that's a risk that you can avoid a lot by staying on estrogen. So we've written a few papers on that. I've encouraged my patients to bring a paper back. And once the OBGYN reads that, then the answer has always been, oh, wow, I'll take care of that. So that sort of covers the big three things that we talk about in my office. Before I begin again, I'd like to make another suggestion, which is I'm more than happy to take questions as we go along. Because of the fact that there are no microphones in the room, I think you have to raise your hand, get called on. I'm about to do so right here. Speak loudly to me and I'll repeat the question. Yes, sir.
So these risk factors for a carrier who's not affected, what about these risk factors for someone who is affected? Does it change their...
Terrific question. Do you ignore the risk factors if you've already gone blind? And the answer is no, because while it's not as dramatic as converting from carrier to affected, I am quite convinced, although the literature is weaker here, but I am quite convinced that some of my patients have had significant setbacks and gone from vision loss to more vision loss in aggravation of these risk factors. So yes, I've encouraged all my patients who carry the gene to observe the risk factors, regardless of their state. And the opposite is also related, which is if you are affected, you have a risk of getting worse. You also have a real possibility of getting better. Years later, some patients get better. And I think avoiding the risk factors has a lot to do with that. I didn't mention the other two risk factors, I'm just reminded. It's smoking, and smoke in all forms, by far and away the most important, but also the issue of alcohol. We're going to probably talk about this in more subtlety. Every molecule of smoke is bad for you. Alcohol is more complicated. It's only when you exceed a certain enzyme that you get into the problem that alcohol has. We can discuss that, but alcohol is a risk factor. And the final one is there are a bunch of poisons out there against bacteria. We call them antibiotics. And if a poison works very well against the bacteria, it can also work very well against the bacteria, the modern version of the bacteria, the mitochondria. You have weaker mitochondria, you want to avoid that. That is not to say all antibiotics. There is good reason, theoretical and in fact in practice, to say certain antibiotics are very safe, others are particularly dangerous. Everybody who leaves my office leaves with a Xerox piece of paper that lists the 5 or 6 antibiotics that we are most concerned about, and you want to avoid those as well. So that's the standard. Well, here we have more questions.
Just where would we, if I'm not going to your office, where would I find that list?
I am sure that your community here can distribute it. I'll be happy to provide a list. I think that Lissa has it up on her website. Where are you, Lissa? Yes, she's waving yes. She has the answer for you.
LHON.org.
There you go. All right, so with that, I think we'll actually start the official formal talk. But we're not at the beginning yet. Can we back up to the beginning? There we go. All right, so sorry. I just want to be a stickler for not that slide, but this one. I think it is important that people know any potential bias that a scientist has when he presents this stuff. And what this says is that there's two groups that are funding clinical trials. And while I don't take personal money, I'm not on salary or anything like that from any of the companies, a lot of research coming out of my laboratories is supported by these groups. And so you should know that when you're thinking about me saying this is a good medication or this is a bad. But don't worry, because I'm not going to say anything that's that good a medication, because there isn't anything that good out there. So, right, what does a patient with Leber's have? Scientifically put, they have these 5 features. They have ultimately symmetric vision loss. Now, it doesn't start symmetrically, but it ends symmetrically. There'll be a lot of variation from this patient to that patient. But once things have stabilized, both eyes are identical, which is, I think, a profound point. And that means if one eye gets better, the other guy gets better. There's just great symmetry. Early on, there's a tremendous loss of color vision. You get a central visual field defect. Maybe that's one of the most important points I can make. Because there's a big black spot in the middle of your vision, several other things fall out. One, you learn that you can see best by not looking at what you're looking at. So if you get into the habit of looking a little bit above or a little bit to the side, you sneak around that big black area. 2, visual acuity, which is a sampling of your vision dead center, is a lousy way of measuring this disease. So yes, most people have very bad visual acuities, but they could have a black area that extends, I'm holding my arms out about 60 degrees or only 10 degrees, and it wouldn't reflect in changes in visual acuity. So we could get a patient much better, and they would tell me, I'm much better, I'm running around, I'm not tripping things, and yet the visual acuity doesn't change. In our clinical trials, we're always fighting this, because the American FDA, and I suspect the equivalent here in Canada, always wants to know about visual acuity, and I always keep telling them, but that really isn't going to change much, one way or the other. So the central field defects are the issue. There is a reason for that, and which is that the smallest fibers in the optic nerve, and the optic nerve, I should mention, is this cable that connects the eye to the brain, composed of almost exactly 1.2 million axons or fibers. And they vary in size, and the disease hits the smallest ones first, and if you're lucky, only the smallest ones. If you're unlucky, it keeps getting to the medium, and finally, sometimes all of them. But it starts small, ends big, and larger is better in terms of surviving this event. And so the smallest fibers give you the center vision, and the largest fiber is the periphery, and that's why. And if you're going to save fibers with the medication or good luck, you're going to save the medium-sized ones, which are in the mid-periphery. And as a consequence, as the fibers aggregate, they come in from the retina like spokes in a wheel, and then they all turn like onto the hub of the wheel. That's the optic nerve. We see a certain pattern in these patients of what we call temporal pallor, and that's a big clue for the neuro-ophthalmologist who knows this disease. He says, aha, both nerves, symmetrical, loss of color vision, central field defects, and temporal pallor. I know that disease. That's Leber's. But most people outside the field of neuro-ophthalmology, and there's only half dozen or so, Claire, how many neuro-ophthalmologists in Canada?
50 or so.
Oh my goodness. I'm so sorry that I underestimated. There's a lot of them. They're behind every street corner. So when you get to a neuro-ophthalmologist, for them it's a snap. They will understand this diagnosis. So I'm obviously going to make up a story here, but it doesn't vary from many of your own stories, and this would be the typical presentation in the United States. Because in the US people move a lot, I think much less so in Canada, usually if there is a family history, the patient's not aware of it because they never met their second cousin from Omaha who has vision loss, and they might assume it's from wearing the wrong pair of glasses. So it's a young man in good health who thinks everything is fine, goes off to college, everything is fine. While in college, joins a fraternity. While at the fraternity, maybe smokes and drinks a little more than he was doing so under his mother's watch. And then around Thanksgiving, American Thanksgiving is the third Thursday in November. When's Canadian Thanksgiving? All right, so our Thanksgiving. Around there's a sudden loss of vision in one eye. So they go to the infirmary. In most places are good enough to say this is real, although I guess about a third of the time, the infirmary says, this is close to midterms, I know what this is about, and don't believe them. But sooner or later, they believe them, and then they tell them that there's an optic nerve problem, and then they work up the optic nerve problems. The most common is called optic neuritis, which is related to MS, and so many, if not most of my patients are told they have MS, and then they do a battery of tests to find out how bad the MS is, and they all come back normal. And then they get confused. Sometimes they go after more serious other diseases like NMO. which also involves more serious treatment like high-dose steroids in the hospital and plasmapheresis and all that, and it's not. And then the second eye gets involved. And about the time that all the tests come back negative and the second eye gets involved, usually around Christmas, they finally say, let's go see a neuro-ophthalmologist. If there was one thing I could change out there, it would be go to the neuro-ophthalmologist right off the bat, save a lot of aggravation, save a lot of money for the insurance companies, but that's the least of my concerns, get things on the right track immediately. So they get the referral. Somewhere around Christmas or New Year's, I often have a chance to see these patients, and we settle in on what's really going on. I put down here, Brazilian presentation is different. We'll touch later on the fact that we have a family, we call them a pedigree, a very extensive family of about 360 people. Not all of them are still alive, but going many generations, which have lived in a cluster in Brazil that we go back to visit every year. That provides us longitudinal data where we really understand the disease. But they don't go blind in November and December. They go blind in April. Anybody want to guess why? I hear mumbling. I think some of you figured it out. It's not so much the college lifestyle and fraternities that gets them. It's Carnival. And so it's their first Carnival that usually tips the balance. And Carnival is in February, and I said a couple months later is when it happens. This is just to remind you about this little thing, the mitochondria that floats around inside of all of our cells, except our red blood cells. And it has 13 different genes that matter. And it can look like this little bean, and it has several copies of the mitochondria, but in most patients, they're all identical. Technically, we call that homoplasmy. Once in a blue moon, there'll be a mixed population. Some will be mutated and some not. We call that heteroplasmy. Most times, if you have that mixed population, that's good enough, and people do not know they have the disease. So that's why I would guess that 95, 97% of my patients who have gone blind and lost vision, it's homoplasmy. But we used to be able to get regular testing for that, and I got to switch labs. I use Athena, and I think Liz has promised to set me straight to a better lab because Athena stopped doing homoplasmy, which maybe doesn't matter a lot to the patients, but matters a lot to me and my thinking. So what's the mitochondria do? I have the simple version in this slide here, which I can't see because of reflection, but I know my slide. Down here in the bottom right, it shows a bunch of molecules lined up in the membrane. Complex 1, 2, 3, 4, and 5. The disease is always complex 1 because it turns out that if you messed up the other complexes, you'd die. But if you mess up complex 1, it's not so bad. And so the electrons get shuttled from left to right on this picture and move down the line. And the last place the electrons go is oxygen, which is why you got to keep breathing oxygen. That's how we get rid of these electrons. But in moving the electrons, which started off with our food and end up in oxygen, which is a way of calling it controlled burning, as this fuel is consumed and the electrons move from left to right, they have little pumps that pump protons from the bottom to the top that produces the battery, which is what the mitochondria does, and then it uses that electrochemical power to make ATP to do all the things that you've got to do. So if you miss out on complex 1, two things go wrong. The one that people mistakenly pursued for many years, and you will hear, is that you don't have enough energy. And that's not true. I bet you the people in this room are filled with energy. All you have to do to have more energy is make a few more mitochondria, and the body knows how to do that. The real trouble is that that electron has to go someplace. And where it goes is it spills out, and it produces something called a reactive oxygen species, or ROS, or free radical. And that signals bad things to happen in the cell. The cell uses it. You need reactive oxygen species. It's not poison, but it has to be at the right dose. And at the right dose, it signals things like make more mitochondria. But at the wrong dose, it signals something terrible, which is called apoptosis, better understood as the signal for suicide. Why would a cell ever want to commit suicide? Because if it's bad and malfunctioning, the body doesn't want it anymore. So our systems have employed a signaling system to say, commit suicide and get out of the way. And we do that all the time. When I was a 16-week-old fetus in my mother's womb, it hadn't been determined yet whether I was going to be a human being or a duck. And I had webbing between my fingers. All you did too. I'm trying to be dramatic here, but it's not just me. And there's no more webbing between my fingers because all those cells in between my fingers underwent this apoptosis, disappeared, and gave me nice little fingers. So it's a nice system. It's supposed to be there, and it took advantage of the fact that 2 billion years ago these bacteria were enemies, and we knew how to kill them, and we knew how to let them kill us, and now we've got it all under control. But it can go haywire, and that's what this disease is about. This process, missed signals, too much ROS, and a desire, mistaken desire to commit suicide all at once by these cells. This is just a more complicated version of that diagram. And this is the story about our visits down to Brazil. So we have these 362 members in 8 generations. Began in 1861 when a young woman from Verona, Italy, was told that her prospects for marriage were not good, so they were going to put her on a ship alone and send her off to Brazil, where somebody had been arranged for marriage. I can imagine the fear she must have had as she crossed the Atlantic. So she arrives to a country that didn't speak Italian, and she ends up in this very rural corner, but they must have done well, because living between these 3 cities, Victoria, Colatina, and Santa Teresa, about 100 miles on a side, that triangle, the whole family has been for the last 150 years. By the way, many people in the family, as we went there, didn't know the story. And one of the most moving things that ever happened to me was the second or third year that I would go down there, and they had a little ceremony in the Civic Auditorium, and they brought me a plate, silver plate. These are incredibly poor people, dirt poor, literally. Most of their homes had dirt. And they had gotten together to buy me the silver plate, and it said, "From the family of Maria Franchi." They, at this point, did understand and organized around this idea that they were all related through her. And this is the first trip. We were in a pretty good clinic, actually, down at the bottom where they had, I don't want to give you the idea that it was that rustic, the most sophisticated clinic in the area, and we were able to use it for a week, plus the technicians and the equipment. The people there were wonderfully generous. Everybody at every stage was wonderfully generous about this. And we realized we needed to get blood samples from all 360, or all the ones that were still alive, 330. And some of these were very old people who were at the top of what they called the mountain, just a very tall hill. And so on a rainy day, we decided the person who was least important in the group, me, because I was director and I had nothing to direct. Everybody knew what they were doing. So the Jeep wanted to go across this little bridge. I said, "There's no way it can make it." I got out and walked together with one of my assistants. By the time I got back, they pointed out that at least half the tire could have fit on the bridge on either side. But we went up the path. Some of you might think that I'm being gentlemanly. I can't see the picture, but I should be holding a big box which carries the camera. It's heavy, but it wasn't generosity. I knew we would be slipping and sliding. I wanted something to slide on. And so we went up the path, and it worked out pretty well. But when I got to the top, I found a 95-year-old woman whose pictures may come up, who was just a carrier, which we thought would be really amazing. Turns out we, as all the patients there, had written permission for postmortems, which is actually an extremely wonderful thing to do. It really allows us to understand the condition very, very much. So she had, and eventually became available to us, and it was like a missing piece to the puzzle that really helped us understand what was going on. But it was interesting going up there. I don't think we have her pictures, but it was interesting because it was a one-room house with a dirt floor, and as I was drawing bloods on the kitchen table, the chickens apparently are attracted to blood, because they all started jumping up on the table and wanted to join the party, which did have a profound effect on me. This is what the pedigree looks like. We don't want to go into detail except to say that's the lady. Oh, I can't get the pointer to work, but not the very center, but near that to the left is the lady that was at 1861 sent off to Brazil. My colleague, whose name should mean a lot to you, he did a fellowship with me that lasted several years, and he's a very close friend and collaborator. It's called Valerio Corelli. Oh, good. He's a really dedicated and brilliant scientist, and when we found that lady came from Verona, he said, "Well, Verona is only, like 100 miles from my house." So in Italy, the tradition is to take August off, and he spent August in Verona, futzing around till he found the right cemetery plots and the right church records, and traced the very bottom part of that group, which is still in Italy. Here's the picture of that lady I was telling you about. This is, like everybody else, a young volunteer. She happened to be in Retina, and most of the volunteers are semi-local. She's from the São Paulo University. And the grit and determination you see in her face is, she's certainly taken many pictures of patients before, but she knew that the lady whose picture was being taken, who was actually unaffected, a carrier, and you can see she's a rather weather-beaten face, but she had never seen artificial light before. Every time the flash went off, she screamed and jumped backwards. And so we're trying to tell her it's not dangerous. And we found some things which were typical, and so we knew our group was not remarkable, but still useful to confirm. The average, we're going to go to the second line, the average level of visual acuity, I don't know if Canadians use the American or the European system, but 5/400 is typical, and the other way of saying that is counting fingers. That's about counting fingers at about 4 feet. That, going down to the second to the bottom, that it happened to have been 4-to-1 males more often than females in this group. But there's a couple of things we found that were not in the literature. The last one was that April was when most people were converting, and you already figured out why. Much more important is the middle line that talks about how the odds of converting depended a lot upon whether your mother went blind or not. And so for the men, for example, if their mother had not converted, it was more like 1 in 4. But if the mother converted, it was like close to 100%. For the women involved, it was close to 0 if your mother had never converted, but it was almost 50-50 if she had. So what that told us is that from the mother, you're also getting the other genes, not just the mitochondrial genes, and the context of other genes, the ones that tell you if you're going to be blonde or blue-eyed, also affected the chemistry in your body in a way that made it friendly or adverse to this problem of reactive oxygen species. Oh, yeah, we'll leave it. No, I guess I do want to go back to another point. We found that the average age, and now I find that the word average is probably stupid. We're going to get away from that. But the average age that men would go blind was 23 amongst our group, which is not far off from what most other descriptions are. You may hear the number 20 or early 20s. And for women, it was 33. But the reason the word average is sort of stupid is it just assumes that there's a peak and a decay, and that actually is sort of right for the men. It goes up, you know, some 10-year-olds, but many more 15-year-olds, and even more 20-year-olds, and then it starts going down in your 30s. But for women, it wasn't like that at all. For women in this group, there was a little bump around 23 also, with a second little bump around 50. And that was our first clue that estrogen protected you, and when women got to menopause, their risk resumed to be higher. And we looked at these risk factors, and I don't want to go over through all the cells of this complicated picture, except to tell you that the 2 big risk factors we found were cigarette smoking and alcohol. And for those of you who want to look at the numbers, the far right-hand column is not the patients that we were examining, but other people in the community that we talked to. We gave the same questionnaire to. About a quarter of them smoked by our definition, and about a third of them drank by our definition. And actually, the drinking definition was pretty high. They drink something very strong there, which is a very cheap form of rum called kasasha. And the average person who did say they drank would drink 1 bottle of this a day. But those are the numbers in the background population. And the numbers amongst the patients who had gone blind were much higher. 65% smoked and 60% drank. And the numbers among the carriers, the ones who had not gone blind but were adults, were much lower than the background. That's an odd thing until you realize, because if they'd drunk more or smoked more, they wouldn't be in that column. They'd be over one column, and they'd be the blind ones. Did I see a question here?
So is that just for the 1178, these percentages?
Okay, so great question. Is it just for 11778? And yes, because his entire family was 11778, so I can't say specifically what the numbers are for the other mutations, but I think the same concept applies. I think that you will find that smoking and drinking, and I say this from hundreds of patients I've seen with other mutations, is going to push your odds of converting considerably. And,
It was like 38 when I lost my eyesight, and I wasn't really smoking or drinking.
I didn't say it's 100%, did I? So, obviously, if 65% of the people there smoked heavily, that means 35% didn't. And so there are people who don't smoke or drink at all who go blind. So please don't think that it's necessary to smoke or drink. It just changes your odds. So I reduce this to 3 simple stories. What happens to the people who are affected after they've been affected? And the answer is they keep getting worse, very slowly and hardly measurable. Then the textbooks had said it happens and it never gets worse because they measured visual acuity. And once you lost the center and you were counting fingers, that doesn't change. But the size of the visual field creeps out. And it does so particularly if you continue with the risk factors. back to the question we originally asked about, should we stop smoking and drinking even if you're blind? Yes, you should, because it can get worse. That, and I don't want to get into the other parts of that, but that's the message I want to leave, that it's still worth being very careful to try to limit the damage. For the people who are carriers, who are fine, they're not perfectly fine. We call them asymptomatic now to make that distinction. They don't have any vision loss in an overt way, but if we look carefully, we can find abnormalities. And these are technical details. We don't have to get into many of them. Even the one that's most obvious, color vision, you can't find that on a standard color vision test. You need a very sophisticated color vision test to see these subtleties of color vision problems. But they do have a minor imperfection that reflects the fact that the very smallest fibers are lost. Just so few of them that the others can easily handle the picture. But remember, it's a wave from small to large, and probably all carriers have lost a few of the very, very smallest fibers. And the third is to show what happens at the conversion. I think that I'm going to skip over this because it's very technical for ophthalmologists, but it shows here a picture of a young man, and this, until this time, had never existed. These would be people who were perfectly normal, who would be followed year after year because they were part of the family. And so we could watch them year after year go through certain changes, subtle changes, that would wax and wane, and sometimes they would wax and wax, and then they would wax, wax, and wax, and then they'd suddenly lose vision. So we got the sense it was a little bit like waves coming and going, and one day the wave gets to a certain point where it crests over the burn, and then you got a flood. And that's sort of what's happening here. Now, I'm going to just briefly say this, but this is a very technical position. This is how it happens scientifically, which is that because of the mutation, complex 1, that molecule that starts things is blocked, which technically could lead to two things: less energy, ATP, and more of these byproducts, ROS. The first, if we measure it in a perfect culture, and we can, some of the cells that we brought back from Brazil got grown in a culture with Valerio and Bologna. It causes per cell an 18% decrease in ATP production if you control for mitochondrial number. But if you leave the cells alone, they make more mitochondria and it doesn't matter. So it's just not an issue. But the generation of ROS is an issue. If you add to that with smoke and alcohol more ROS, and that's what happens when you smoke, you're breathing in a tremendous number of ROS. If you drink a little, you're not, but if you drink more to the point that you get buzzed, that means your liver's not handling the alcohol, you make ROS, then it gets over a threshold. And when that threshold is achieved, something remarkable happens. The rest of your body doesn't care. It's only certain cells that do. And the cells that care the most are the brain cells. And the most vulnerable of all are the brain cells that have these things called nodes of Ranvier. And without getting technical, there's one giant node of Ranvier, much bigger than any other in the body, and it's in the eye. And that's why it's the optic nerve. That's the first and usually the only thing to go. You may ask us later on, is there such a thing as LOH+? And of course there is. LHON plus means in addition to the eye, something else happened. It's the exception, certainly not the rule. Perhaps there's one or two of you in this room who've had that. But it's 98% about the eye, and there might be a little bit of a peripheral neuropathy. There might even be some funny little EKG on the heart, but more or less, it's about the eye. And it's because of this node of Ranvier thing that the fibers in the eye don't use myelin because of the optics of the eye and the fact that myelin's not transparent, and it's at a cost that that happens. And this is a cartoon of mine that shows that. And just to briefly talk about the cartoon, complex 1 doesn't pass an electron. No problem. Complex 2 donates an electron to 3, and 3 to 4, and 4 to 5, and the system works. That's why all the mutations, although they're different, all affect complex 1. Because if they had affected complex 2, 3, 4, or 5, it would have blocked the whole system up, and this child would never have been conceived and never been able to live. They would have been lethal. So in a sense, LHON represents a genetic mistake of the very mildest possible sort, which is compatible with life. Then you get a lot of ROS, and if you aggravate that with tobacco or alcohol or antibiotics or something that gives you more, it tips the balance in the mitochondria. The mitochondria is supported by other parts of the cell so that if you're lucky, it's not too bad and it doesn't really tip it, but if you're not, then the mitochondria put out the ROS that signals apoptosis, time to commit suicide. And the cells somehow communicate. We're only beginning to understand how, but if a cell or two dies, it does it alone. But if a bunch of cells decide to die, then they bring their neighbors in with them, and they say, let's all go together. There's obviously a need for the body for us to get going. This is a very useful system. It's estimated by some that about once a day, one of your cells turns cancerous. We're all flirting with cancer. But when a cell turns cancerous, 99.999% of the time, your immune system picks it up and tells that cell, you're misbehaving, kill yourself. And it does, and that's the end of the problem, called immunosurveillance. So this process of signaling so that the body can get rid of bad cells is a very good thing. But in this case, it gets out of control, and a bunch of fibers tell each other, I guess we're not wanted, and they all die at once, and that's the attack. So these are questions that I started off 30 or 40 years ago that fortunately we could answer, which is why of all the tissues in your body is it the optic nerve, and it has to do with this thing that the brain, and the optic nerve is part of the brain, has a very, very high energy need, and so it does a lot of this stuff. And myelin really helps protect that energy need and makes it less. And the optic nerve doesn't have myelin in this particular section in the eye, and so it does it more. And even within the optic nerve, it happens as a wave. This is work that came out of a Brazilian study from another great colleague of mine from Italy, Piero Barboni. And what it shows is that the first fibers to go and located in this area called temporal inferior, and it's not a coincidence, those are the smallest fibers in the eye. And then the very last fibers to get involved by this technique called OCT is supranasal. They're the biggest fibers in the eye, and they go as a wave from small to large. And this is just an actual picture. The picture on the left has been reproduced by counting fibers in a normal optic nerve, which one of my postdocs did in a very tedious study of 100,000 measurements of these little fibers. And he shows that the smallest fibers are inferior temporal and the very largest are superior nasal. And this is an actual optic nerve from a patient with Leber's, average patient, where the dark stain stains the fibers that are intact. And you'll notice that the picture on the left, which was generated in theory, and the picture on the right, which was generated by nature, are a really good match for each other. So I'm going to move to the second part of this lecture, if you want me to. Let's take the question first.
Yeah, hi. Can I just ask a question? Because, sorry, the interesting thing about Lhon is that it's kind of one of the few blindnesses that's reversible, right? So if we have apoptosis, means cell death, it's not always cell death, right? Because you get, because I don't think we can regenerate.
Okay, excellent point. So first let me agree with your assumption. You're born with 1.2 million fibers, and never in the history of this planet has anybody gotten an extra fiber added. You do not regenerate fibers. It would be, not only it's important to understand it for your question, but important if anybody here asks me, well, how about stem cells? The reason we don't regenerate new fibers is not because we don't know how. Biology knows how. It's because the wiring has to be so precise. It would be the equivalent of saying, I cut the cable to my TV set, no problem, I'll just solder the two ends together. You know, it's got to be the right fiber to the right fiber. So if you've got the right fiber growing in the eye, but it didn't go to exactly the right place in the brain, it'd be causing more problems, not good stuff. No, we don't regenerate, you're right. So how could anybody get better? It's a great question, one that we pondered. Not only do people sometimes get better, but they usually do so 1 to 2 years later. 1 to 2 years after they went blind in cases of spontaneous remission, which, just so we can get this out there, for most mutations almost never occur. It's about 4%. But there is that one mutation that I said, if you're lucky here, I don't want people to raise their hands, but anybody out here is 1444, then okay, count your lucky stars. Because that's the one that has about a 40% spontaneous remission rate. And even though that's the official number, the reality is that depending upon what you define as getting better, it can be as much as 90%, a little bit better. So what is going on? He's not growing new fibers. He's got fibers that are dormant. So there's 3 states you can be in. A fiber that's alive and healthy, a fiber that's dead and gone, and a fiber that's dormant. And quite mysteriously, that dormant fiber will sleep for a long time. And you're going to get towards the end to where I like to use idibanone. And if the idibanone works, we don't know it for a year. Because even in the patients that it works, it's a year later that they start to work again. And this is just theory, but my theory shared by Valeria Corelli is that when the fibers stop firing long enough, their supporting cells in the brain, called oligodendrocytes, quit on them. And therefore they have no myelin. And a fiber without myelin needs more energy than ever to be able to fire. And even a normal fiber can't manage it. And now these guys are behind the starting line with an inability to make energy. It's hopeless. But if you just wait and the fiber recovers, once in a while it'll get enough energy to make a little connection. And then that'll tell an oligodendrocytes in the neighborhood, maybe I should pay attention to this guy. And then maybe it comes up and touches against it while it fires a second time. And this thing that we call a stochastic process, bit by bit, these two start to flirt with each other, and then they finally marry each other, and then they finally make kids, and that's a fiber that can fire again. And so that's the recovery process. But that's the exception, not the rule. Let's not think that most patients with labors get better, because that doesn't happen yet.
No, that wasn't the point. I think it was to say that it'd be an interesting research to kind of to figure out because it's a very interesting process. It's supposed to be apoptosis, and it's not. And for vision in general, I guess I'm thinking this is a pretty remarkable process.
So of course it is, and you're absolutely right, and you can bet that right now is my #1 goal to address that issue. But the other point that's I think worth saying is that we have some redundancy in our system. And I always told myself I wouldn't put it this way because certain political reasons, but there is redundancy. There are more than one fiber that has the same job. And so if you lost 90% of your fibers, you could manage rather well. But you lose 99% and you can't. So there may be a relatively small extra zone of dormant fibers, that 9%, that if they can come back, you can do very, very well. So this is the list of things that we're doing to treat the disease. And I thought I could dismiss some of them relatively quickly and out of hand. Things like vitamins and coenzyme Q10, I have no problem with them. And if you have access to nothing else, fine. But they don't work well. If they either don't work at all or they work very marginally and we can't measure their advantage. So we have worked on this particular chemical called idibinone. Now idibinone is coenzyme Q10 with a plus and a minus. Coenzyme Q10 is what nature gave us to deal with that spilled electron. It picks it up. And sometimes it even redirects it back into the system. So why doesn't coenzyme Q10 work? Because it can't get into the mitochondria. It's one of those things that gets trapped by membranes. So if you eat a lot of coenzyme Q10, one or two things happens. Most likely you make very, very expensive urine. It just goes out of you. Possibly a little tiny bit immeasurably gets in and helps you. So idibinone is coenzyme Q10 minus the huge long tail that is what blocks it in the membranes. Idibinone does get from your gut into your blood very easily, from your blood into your cells very easily, and from your cells into the mitochondria. All the places the coenzyme Q10 is screened out, it gets in. But nature gave coenzyme Q10 that long tail for a reason. It's much, probably 1,000 times more effective at shuttling electrons than idibinone. But the idea is you can make up in numbers which you don't have in quality, so a lot of idibinone probably helps a little bit. All the experiments that we've done in cells and in patients support the idea that idibinone helps, although I don't want to exaggerate. It helps some patients a little bit. With that in mind, we went to another chemical, Epi-743, made by something called Edison Pharmaceuticals in San Francisco. They don't make it anymore. And it never was FDA approved. So I don't want to get your hopes up. But the idea was to make the molecule with a medium-sized tail, shorter than coenzyme Q10 so it gets in, longer than idibinone so it does a little bit more work, with a couple twists in the tail to try to take advantage of that. And it probably is in between, and so it's a little bit better, but it's not available. Then we're going into the world of gene therapy, and I'll talk a little bit about that coming up. It's great in theory, but the home run has not been hit yet. And a new agent that's being made by some people in Massachusetts by a group called Stealth, MTP-131. I am very excited by it. I like the theory. I like some of the stuff they've been able to do with it. The biggest problem is it's similar to the problem of coenzyme Q10, which is if you can get in the mitochondria, it's probably great, but it's not very easily transported. Yes?
Hold on.
Yeah. Slow down, Lisa. We got all money. I don't want you tripping here.
Why is it that second medication you spoke about isn't available anymore?
Well, it was never really available. When a drug company makes a medication, it puts in millions of dollars of research. It tries to test it, and then it has to make the decision whether to go ahead with a clinical trial, which costs many, many more millions of dollars. And more or less, we ran a trial with, I think it was 21 I'm getting confused, Rustin knows. A handful of patients were tested on that medication. And the company actually is very, very moral. It continues to make the medications for those patients so they're not left high and dry, costing them $500,000 a year, but they don't want to go forward with the clinical trials because they look for a home run, and it was a bunt single. It made a few patients a little bit better. It was not nearly as dramatic, and they just didn't think that it was going to make it in the market. Now, once that happens, without the clinical trials, the FDA is not going to approve it. Or the American FDA, but the European and Canadian equivalents also won't. Okay? So if you want, and I actually leave it up to the group, we may have gone long enough and we may want to just quit right here, or we can go into a little more detail about these clinical trials. Cut. I think we're done. Yeah. They're in charge.
We'll have a panel that will cover and we'll do Q&A right after.
I think Kevin said we were stopping. What were you saying, Kevin?
Can I ask a really quick question?
There will be a Q&A with 3 neuro-ophthalmologists.
That's fine, no problem.
That's okay.
Sounds good.
All right. Well, at that point, then, I'd just like to tell you how proud I am that you've come together, how pleased I am that you've been kind enough to invite me, and I hope that I'll have a chance to do something like this again. Thank you.